There we go.
Garage.
Okay, I think we're live, guys.
Okay.
Okay. Let me open the correct window so we have something to start with. There you go. Okay. What I did in relation to the model I was building yesterday and the days before was I removed one camera and mirrors, and just for the simulation's sake, it's easier to use two cameras looking straight down the barrels. You know, the displacement or the aberration of the actual particle is going to be in a straight line then, and that's easier to measure and to demonstrate and explain actually what's going on, and etc. What I created 4 models for each scenario. This is the stationary, the control mechanism, so to speak, with a stationary light, stationary telescopes, and then in theory and in reality, the light particle should fall straight down and hit the center of both tubes, and you know, give zero aberration. And I can show that. Here are the 2 particles, red and green. In a no water camera, it will come straight down the barrel and hit the bottom of the pipe in 1 second exactly. I'm going to freeze frame there. There you go. Let me render this. You have the light exactly in the middle of the screen, vertically and horizontally. And then the same for the water-filled camera, which is going to hit the bottom a little bit slower, of course, because it has to travel the same distance at a slower speed. And the actual time difference is, of course, it's exaggerated in relation to reality, but it's still, you know, the concept remains the same. And it hits the bottom at 1.04 seconds. And then the same thing, there is no aberration. If you put these 2 images on top of each other, you would get the benchmark result. Where is it? Here. The red and green are overlapping each other, and you don't see any change. So that's our control. This is what we should see when the light is stationary and the camera or the telescopes are also not moving. Then there is the second scenario, which is the Earth's rotation. I've got that set up here. Let me just show that from the side view so everybody knows and sees what's going on. We have the 2 emitters here on top, and they are stationary, and the telescope, the 2 barrels are moving side by side, and as soon as the telescope is exactly in the middle of the setup, the 2 emitters will drop a particle, and then the telescope will keep on moving, and then there will be aberration, of course. And the difference in the aberration is going to show what the concept of Airy's experiment actually meant. So let's drop the particles. You can see that the scopes are moving now, or at least very slowly. Let me go to the no water camera.
Can you hear me?
And then at 1 second exactly, there's going to be a particle released from the emitter. There it is. It's falling down.
My audio working here? Check. Can you hear me, Mike?
Yeah, I can hear you, but you're very faint.
Okay, it's too low or?
Yeah, a little bit quiet.
Yeah, I'm trying to turn it up here. Is there a way to time to calculate what the time difference would be going through 2 meters of water?
You mean with this setup or in reality?
In reality? Well, either way.
Well, in both scenarios, you would have to, lower the speed of the light by the impedance of the medium it's going through. And in the case of water, that's 14% speed reduction, which gives
40?
you an offset in time, and that offset in time is your aberration.
Yeah, that's what I was wondering, if we could calculate what that would be in reality.
Yeah, well, Airy calculated that there would be an aberration of 14 arc seconds with his setup, and I'm not sure about his dimensions, what the actual vertical length was of his water-filled tube, but I think it's very easy to calculate actually.
Garage.
Okay, well, let me go on with the setup. The particle is going to hit the bottom of the barrel at 1 second exactly. It's 2 seconds in time because I've released the particle at 1 second, and that's when the emitter was exactly in the middle of the crosshair. And now the particle will be at the bottom at 2 seconds exactly, and you can see it's off the center of the screen. If I render this, then here's the center of the screen, and the actual light particle hits here. This angle is the aberration from this setup. And now I go to the water-filled camera, and then of course the particle needs 0.4 seconds to actually be at the same position. So let's scroll forward in time. There it is. And when I render this, it's roughly at the same position, you would think. But if you overlay these two images, let me go, where's Earth rotation? Here, Earth rotation aberration. You can see that they do not exactly overlap each other. There is some individual aberration between the two. And that's what Airy's setup was actually testing for. If the telescopes were moving, you would get this individual aberration between the empty pipe and the water-filled pipe. Mm-hmm. And if you repeat the same concept, but now with an ether wind, all the angles of this setup of the ether wind are arbitrary, and they're just to show what the actual result would be if the light is coming in at an angle. Let me go to the no water camera first. The particle is going to land. First, again, the particle is going to be released at 1 second exactly. Let me select the correct emitter. As you can see, the angle is 0.1 degrees off perpendicular, which creates the angle of the light. And the reason I did that in this way, I typed it in the notes yesterday, is there's two ways of actually getting the same result. But to change the vector of the perpendicular light is by creating a wind object, and that will create a diagonal stream of the particles by blowing them to the side. Or the easier way is to just tilt the emitter so it drops it at an angle from the source. Let's continue. There you go. The particles are dropped. I'm going to freeze it at 2 seconds. Go. Volume is low. Yeah, I can't help that. My microphone has one volume, and that's loud.
I hear you fine.
Yeah.
I think it's okay.
One more frame. Okay, now this is the aberration with if the star was actually the one that's moving. And then we have the water-filled camera. The light particle, so to speak, is not exactly at the bottom of the barrel yet. It needs that 0.4 seconds again to reach that same location. Let's scroll forward in time again. There you go. If I render this now, that's where the green particle is. And if you overlay these two, where is it? Here. With the ether wind, you'd see there is no individual aberration between the two particles. They land at the same position relative to the center of the frame. And then there's another scenario, basically not using the supposed assumption of an ether wind. So, the stars are moving, but there's no wind dragging the particles along, which, results in a no vector change of the light. And I've created a scenario for that too, with no ether wind. And you can see the emitter is now pointing straight down again. There's no angle involved. And it's moving, as you can see. I selected it here, and it's moving towards the center of the barrel. And at exactly 1 second in time, it's going to release its particle, and that particle is going to drop down. And it's going to hit the target at 2 seconds exactly. There you go.
What did you set the frames per second to?
1,000. No, it's easier to work in units when you have your emitter is at a specific distance, and if you use the same distance as speed, if it's 500 centimeters up in the air and you use 500 centimeters per second, then the particle will be at y0 at 1 second. And there's actually a little bit offset in that, and that's 0.26 centimeters. I don't know why that is, but you have to increase the altitude of the emitter and then drop the particle at 500 centimeters per second. And then if you use this figure, it will be at exactly y0 at 1 second in time. And now the reason these are a bit offset is I can demonstrate it in a new file, and it's easier to understand then.
Does that have something to do with the size of the particle reaching like the center part?
No. If you here's the emitter. Let's make it very small, 1 centimeter by 1 centimeter, and let's create spheres as particles. And let's make them 10 times the size of the emitter. Smooth particles. Put them here, and then go to the emitter, and then show objects and do tangential. If I now press play, you see they will if I increase the speed of this, where is it? Speed. Let's make it 800. I'm not sure why it's so slow. But you would think if the wait, I know why it's so slow. There you go. if the emitter is 1 centimeter large at the moment, and the particles are 10 times the size, so you would think, you know, that if they are emitted from the emitter, that they will all be in a straight line on the Z or X axis. And you know, if you can look behind them, they're actually not all appearing from the same position in the center of the emitter all the time. There is an inconsistency in that. The fact that they appear at a different position in the X, Y, and Z grid from the emitter itself. But the only thing that is consistent is that, you know, all particles in sequence all appear at the same position in the emitter. So that's why in my setup, if I go to my emitters and I go to the coordinates.
And the emitter doesn't have any size or anything. I mean, what options are on the emitter?
Well, you can make the emitter a specific size, but you know, that doesn't really do anything to the particles. As I showed, my emitter is 1 centimeter X and 1 centimeter Y, but the spheres that are coming out of it are 10 times its size. So
yeah.
you know it should in reality it should be actually like pushing them outward through the center, but it's not doing that.
And what if you make it like 0.1 or 0.01 centimeters? I mean, maybe
doesn't matter. You know, you can make it a micron in size, and it would still do the same thing. It would still emit in a sequence, and you know, there would be an offset between each particle. You know, and it's a problem that you can overcome just by offsetting your emitter in this setup, so that the first particle it drops is actually dropped when it's at exactly X and in this case Z0, and then it drops down on the Y axis.
Oh, I see.
And that's what I did. You know,
the emitter types. What does that do?
Sorry?
The emitter types, like you have pyramid.
Yeah, well, I've tried both. You know, you have pyramid and cone, but I've not seen any difference in the emissions from both types. So you know, I'm not sure why there is a difference in type.
And the help doesn't say anything about it?
I haven't checked the help. You know, I don't take the time to read all that stuff. I just find the solution and then continue.
Yeah, but you know how to find help on each item, right?
Yeah, sure. It's
control click it. No, not up there. On the emitter type, if you control click it or command click, I don't know if it's different on PC. Control click where it says emitter type. Yeah. Should pop up a menu. And at the bottom of that menu will be help just for that. It's contextual help.
I'll show help here.
Did it work?
Yeah, here it is.
Oh, it's just slow coming up. I don't see it yet.
Yeah, it's your connection.
Yeah.
But you know,
that's the way I always get help, because it takes you right to the place, you know.
Yeah, well, I'm looking at the page now, and I remember reading some of this stuff, but you know, in this setup I've overcome the problem of inconsistent emissions just by changing the offset or offsetting my emitter slightly off its center so that it drops.
So the emission angle you have is set to 0, I guess, right?
The emission angle. Well, the emitters themselves are positioned to drop the particle down, either you know in the Earth rotation setup straight down, or with the you know the setup of the ether wind at an angle, and the angle is arbitrary. You know, the 0.1 is something that I just chose because it worked. You know, you can use bigger angles, but then you would have to change the speed of the particle itself also.
Because then that helped, like the window just came up and then went away pretty quick, but I saw emission angle. I don't know if that's something that pertains to the shape of the emitter.
I'm not sure.
I thought maybe,
but you know, for these 4 scenarios, you know, the emitters are actually functioning, that they're doing their job properly, because
okay.
I've shown that in the benchmark setup, you know, the control setup where it drops the particle and it lands exactly in the center of the screen.
Yeah, true.
So these are basically the four scenarios with two pictures each, and one picture combining them. This is the benchmark. Both particles are both at the center of the screen. There is no individual aberration. Then you have Earth rotation aberration, where the green one is a little bit higher than the red one, and that's because it's the scope is moving, and it's moving at a slower speed, so it arrives at a different position.
So how long do you think it'll take you to build this?
In reality, you mean?
Yeah.
You mean to actually build the scopes?
Yeah, of course.
Wow. The PVC itself, I got in my workshop, and I just have to order 2 pieces of optically clear glass, glue them on top, and make sure that they don't leak or pop off when we put the water in. And then mount 2 precision mirrors on an adjustable setup. Make a contraption so it's dark inside, and then at the end of the contraption where the light is combined, make an adapter for a 4K Canon camera and mount the camera on top, and then basically you're ready. So I could build it in a weekend, so to speak. But I'm
so these 2 tubes, their combined width is gonna have to be smaller than that lens mount, right?
Yeah.
Yeah.
Correct.
And the top, you could put 1 piece of glass, which would actually serve the purpose of joining the tops together. Of course, you probably will have them joined all the way down the spine, but you could use just a single piece of glass on the top, because you're probably going to want glass on both of them.
You also put glass on the empty tube? No, I don't think so. The empty tube needs to be empty.
Oh, just to remove any doubt that the glass might be causing any sort, to keep them equal,
Well, technically and theoretically, just a thin piece of glass would, create the aberration, because the light is being slowed down as it moves through the glass, and then speeds up as soon as it exits the glass. And so that slight moment of speed decrease should show up as an individual aberration, but that's probably too small to even notice or measure.
Mike, can you explain? On the top, you have this this mirror what splits the light in these 2 tubes, and on the bottom is the opposite. Is it going to together again and then into the camera, or how?
What do you mean?
So how the camera is recording this? I don't understand this till now.
Well, in this simulation itself, the cameras are just at the bottom of the barrels, and there are 2 cameras because for the setup and explanation of this, it's easier to explain with 2 different cameras. But in reality, you would have to mount these cameras at exactly the same position, aligned perfectly, and they would have to be optically, the same, and that's technically almost impossible.
2
so
cameras.
That's why I'm going to use 1 camera and then combine 2 images on the frame side by side, and then you can see if there's individual aberration or not.
Also on the left side is one. You will see 1 tube, also the picture from 1 tube, and on the right side the other tube.
Yeah, correct. Yes.
Okay, thank you.
And with stars, if I place these tubes straight up side by side and I point them to a star, both tubes will see the same object, but they're split in 2 and then placed on the camera frame as 2 separate images, but they're actually the same. One is going through water, and the other one is not. And if we're living on a rotating Earth, then I just demonstrated that there should be an individual aberration between the 2 stars on the screen. They should not be aligned. And if that's not the case, then the other two or the other hypothesis comes back into play, and that's the ether wind.
Okay, Mike, I got a question for you. On our baseline control test, we're going to have a single point light suspended and rigidly fixed up above the tubes by about, well, how high is your warehouse? We can get about 3 meters above it or 4 meters above it, maybe.
My workshop is 12 meters high, so.
So with the tubes being 2 meters, then we can have it, you say it's 12 meters high?
Yes.
Okay, great. So we can have a good 4 meters above the tubes, the light, right?
Yeah.
Okay, so if we have that, and the barrels are going to be about 80 millimeters or 55 millimeters across.
I put the diameter of 10 centimeters, and with PVC, that's most of the time it's the outward diameter, and then you have the thickness of the material itself, and then the inner diameter is about some centimeter smaller.
Yeah, so 10 centimeters is 4 inches, so there'd be two basically 4-inch tubes OD.
Yeah.
And then so the center of both tubes are 4 inches apart, right?
Yeah, correct.
Right. So my question is, does that parallax from say 3 meters above the scope, is that going to actually be a different view from the stationary?
The problem is with the local stationary light, there is, you have the issue that you're not seeing the light in the center of your tube because
Right.
It's too close and too small. The bigger you make your object, and the further you put it away, the less that becomes a problem.
Right.
But for the stationary test, the lights, you could basically make two lights that are exactly 10 centimeters apart, the two centers of the two tubes, place them on top, and then align your mirrors so that you have them in the specific grid line on your camera, and that's then your control measurement. It doesn't have to necessarily be at exactly the same center, so to speak, but it's it's a position from where you can then start measuring your next setup.
So the question then is, the light from a star, does 10 centimeters make a difference? Can you actually see the star the exact same place in the bottom of the tube?
Oh, well, yeah, the example is Steve asked the same question a couple of days ago, and the example you can use for that is the viewfinder or the aiming scope you have on top of your regular telescopes. Those are two tubes. They're both pointing in the same direction, and they're seeing the same object in the center of the screen.
Right. Okay. That's true. Okay. I mean, the one is vastly
But in
more.
that example, Mike.
Sorry?
But in that example, Mike, the viewfinder on a telescope, it's adjustable. So I mean, you make it.
Yeah, correct. Yeah, well, but technically, if the object is, let's say, 1,000 kilometers away, and you have two tubes that are pointing in the same direction to that same object, if there is any parallax between the two, then that means that the object is smaller than the two diameters combined.
Okay.
And with stars, at least, we know from experience that if I'm at, let's say that the center of this tube, the bottom, is a GPS position, and the center of the bottom of this tube is another GPS position. If I go look up how much of an angle I need to put my telescope to see the object that is supposedly 90 degrees on top of that, they will all have the same angles. Now, and even if you put them 10 meters apart, you would still have them at 90 degrees pointing straight up, and they would still see the same object.
Really?
Would it be interesting once you have this set up? I don't know what the speeds would be, but it would be interesting to move the ground east or west. Move the telescope. Get what I'm saying?
Not really.
In other words, we know the ground is not moving and it's a sky that's moving, but to see what the results would be, you could simulate a moving Earth.
Well, of course.
Set your camera and the whole apparatus on some sort of very controlled, I don't know, using stepper motors, because I don't know what the speed would be, whatever the speed of the Earth is. Actually, it doesn't need to be the same. We just need to create some similar movement and then see what your aberrations are.
That's exactly what we're going to do. There's 3 measurements from 3 different paradigms. 1, nothing's moving. 2, the light is moving. 3, the telescopes are moving. And definitely
can we assume nothing is moving? I mean, something is moving. We know that.
We set up a light and we set up the telescope, and they're not moving relative to each other. And then we see where the light falls in the 2 scopes. Right. And we see, that's what Mike says, 0 aberration. We have no vector, no sideways vector on the light, because there's no relative movement between the light source and the telescope. So we verify that light just goes straight down and they both hit in the center, done. And then we move one of them, say, let's see how they shift when the source moves. Now let's see how they shift when the telescopes move. Because we have 2 different medium of refractions there, they should be different. And we're going to observe that they are different. And then we say, now let's look at a star, real life. Which of these models does it?
Yeah, well, this simulation explains the concept behind this, and then we scale it up to do the local test and see if we can actually detect any aberration. I'm not sure if that's doable, but I could be wrong. But at least with stellar aberration, it's a known phenomena. So we know that it's present there. So with this setup, the same as Airy, basically, only Airy had an empty telescope and then did the same test with water in separate days. And we can actually render a result instantly. And we would see aberration, and we would also see individual aberration in the same frame, because we're looking at the same object.
Mm-hmm. And you think you would get different amounts of aberration if you were viewing a star, say, overhead versus a star closer to the horizon? It would be moving faster, I guess, right? Like if you were viewing.
Well, usually the stars that move over on top of you overhead are the ones that move the fastest relative to you. So I think that would be.
I'm referring to like a star that's at a lower latitude than you.
Yeah, well, I think that's why I wanted to create the parallel surfaces. This setup is just using a star that's moving directly on top. But I'm very curious to see what would happen if you do the same with a star that's at the 45 degrees elevation angle, for example.
Right. Not necessarily coming at you, but a star that is south of your location.
Yeah. Because
if it's stars going around, in a plane, then it's going to be probably moving faster.
The aberration based on your angle towards the object should be different, which direction you're looking. So it should, it would be a good test to see if there is any consistency in the aberration if you're looking at the northern star and then at a southern star, for example.
Right.
There's lots of fun stuff and interesting stuff that we can do with this this setup. But the first thing we need to do is to get it actually working. Because it works fine in the simulation, but real life is a different story.
We could even eventually try it on an airliner, a known moving source, and see what we get.
Yeah, well, yeah, yes, absolutely. But trying to find aberration in an object that's going to move through your viewfinder at a very fast rate is difficult.
Yeah, it's gonna be shaking around so much.
Well, yeah, you have the motion blur, for example. If it's moving very fast and you need to take a single frame of the object, how are you going to avoid the motion blur, which is going to look as aberration?
How would we
just
do
need a very fast frame rate?
A video thing, and through water and through air, those things should separate, right? Or should not separate. Moving object up there. See, that's the idea.
Yeah, well, that's something that we could actually test with Cinema 4D.
Yeah. Well, that's exciting work. That's great.
Yeah, well, this simulation is, that's why I wanted to build it myself. I've seen Michael Bowden's video and explanation of this, and the mechanism of what he's showing looks solid, but I wanted to test it myself if it actually works in a 3D simulation with all the right conditions.
We should do a short video, basically a cleaned up version of what you just did here, with somebody talking. It can be something, very quick, 3, 4, 5 minutes, just showing where we're heading.
Yeah.
Showing the different results and to get people starting to see what's going on.
Yeah, well, that's something I'm for, of course, but let's first fill up a pipe with water and seal it off with glass, and then try and put a camera in front of it and see what you see. If the objects are blurry, or we need to use demineralized water, for example, or
distilled water.
Yeah, there's another liquid, or maybe a gas, but I'm not sure if that would create the same impedance. But there's lots of stuff that we need to figure out. But now that I've verified it for myself, at least, that this is a viable concept, I'm very eager to put this to the test in reality. And
there's even when Stefan asked the question, do we know that light moves more slowly? And that is the definition of refraction. And there are refractive substances. There is a certain type of quartz glass laced with gold, doesn't take very much, or with lead or other substances, and you can change the speed of light like 25% or even 40% on some of these substances. And that brings to mind is we just get a filter made out of that glass, and voila, there's your big tube length. You just got 2 filters, and then combining the images.
Oh, no, because it's the surface area of the medium that's creating the impedance. That's very important. You have to create as much surface area as possible, because you want to slow down the light over a larger distance to create the actual individual aberration, because else it will be undetectable.
Now, you mean the depth?
I thought of the same thing, Robert. I asked Mike the same question a few days ago.
Well, but I mean,
the length that's important.
Yeah, the length of the impedance medium. That's very important, because that's your actual, that's going to create the offset in time, and that's the aberration that you're.
Oh, I agree 100%. But my question is this: light is 1.14, right?
What do you mean? Water.
Well, the refractive index of vacuum is 1, right?
Yes.
And water is 1.1.
Yeah, air down here is like 1.0003 something.
Water is 1.33, and I can show that. There's
Okay. 3.3. Well, that's a good stiff index. Okay, great. So yeah, we have a lot of slowing down of 2 meters of 1.33. Okay, because I don't think these things are that much slower, and that then tells me this is speed of light to the moon and back is what are we actually going through? What is the refractive index of if there is a firmament or of the waters above? What's the refractive index? We don't know. And so 2.75 seconds to the moon and back actually might just be the result of the refractive index, and the moon is still not very far away.
possibly, yeah.
Yeah. Okay, great. Yeah, sounds like water's a good bet then.
Yeah, water or glass. I think glass has the same. Let me see, glass. No, glass actually has a bigger refractive index, 1.517.
There's actually some wacky things. You have a 4 point something or other refractive index.
Yeah,
I believe.
I think that will also create distortion in your image, and then it's difficult to actually do any solid measurements.
Yeah. Well,
alcohol has about the same index as water, I think, and it maybe would be more clear. Maybe create less distortion.
Yeah, but just alcohol is dangerous stuff to work with.
Well, as long as you're not smoking around it, it's sealed up anyway.
Yeah, you're telling that to the right person.
Create a cannon.
Oh, let's just use water. Water is not flammable. It doesn't have any explosion damages or danger. So.
Yeah.
Now, and 1.333 is a speed reduction. I think it's 14%. Let me just check that. Speed reduction light through water. Yeah. Okay.
0.75. So the speed through water is 75% of what it would be in a vacuum.
Yeah. And glass is actually now a third. It's 200,000 kilometers instead of 300,000. So, but getting a 3 or 2 meter solid piece of glass.
Yeah, good quality, impossible.
Yeah, and just demineralized water would be the easiest solution, I think.
Silicon carbide glass. Silicon carbide laced glass has 2.65. So compared to the 2 meters, 2.65, I don't think it's going to do anything for us.
No, and that's why water is if Airy if Airy's calculations came out to a 14 arc second difference in aberration based on the length of his tube, then that's detectable for us also. With we've got 4K cameras, digital equipment. If we use half the length of his tube, for example, that would in theory or have an individual aberration of 7 arc seconds, and that's still measurable with digital cameras.
That's great. Good. We're on the right scope spot there.
Yeah, so all we have to do is figure out how to get both images in focus on the same camera, and have that as a benchmark to do aberration measurements.
we could go to NASA and say, how do you keep your water so clear on the ISS shots? So they could tell us.
Yeah, well, maybe they know.
I'm sure they know. I'm sure they know. Just you got air bubble problems only. That's the only problem sometimes.
Okay, well, I think that explains this model now, and I'm sure everybody that looks back to this or has seen it now understands what this concept entails and how we're going to repeat this test. And you know, if somebody out there has some good advice or tips, or maybe something that we've missed, or wants to add another scenario, then please please email us, and I always respond within a couple of days. So that's it for me, guys. So do you guys have anything to add or any questions to ask?
I'm okay.
That's it? Okay, well, thanks, guys, and then I'll stop the stream here.